In this video we're going to talk about relations and functions as well as domains and ranges. We've been talking about relations for at least a couple of years now. A relation is simply a set of ordered pairs, and so an example of a relation is a straight line. A straight line is an infinite number of ordered pairs that form a line when graphed, and we did that quite a bit in grade 9. In grade 10 we talked about parabolas. A parabola is just an infinite number of ordered pairs, and when we graph each of those ordered pairs they take the shape of a parabola. So a set of ordered pairs is a relation, and specifically values of the independent variable x are paired with values of the dependent variable y. And we can express a relation pictorially, algebraically, or graphically. For example, in grade 9, algebraically we expressed lines in the form y equals mx plus b. Graphically we expressed lines by literally graphing them. A domain is the set of all the values of the independent variable of a relation. So in other words, all the x coordinates, all the possible values. And a range is the set of all values of the dependent variable of a relation. So for instance, that is the set of all possible y values of the y coordinate. And the domain and range are usually stated in either set notation using brace brackets or interval notation. We're going to focus on set notation for this note. What we're going to do now is determine the domain and range of each of the following relations. The first one is given to us in the form of a mapping diagram, where the x's are listed as -2 and 1, and the y's are listed as 4, 5, and 7. Well, we see that the possible ordered pairs are -2, 4, as well as -2, 5, and 1, 7, because that's how they're indicated with the arrows. So we have 3 possible ordered pairs here, but our domain only has 2 values. Our domain has the values -2 and 1, and so we say the domain is the set of -2 and 1. Our range is the set of 4, 5, and 7. And so that is how we would indicate it in mapping diagram form. That's how we would state the domain and range of a mapping diagram in set notation form. Now, if we had the function itself given to us in set notation, so for example 5, 1, 2, 3, and 4, 1 are our 3 ordered pairs in our relation, then we could say that the domain is equal to all the possible x values. In other words, 5, 2, and 4. So we could say that the domain was the set of 5, 2, and 4, but we tend to read from left to right, and so we state things in the numerical order from least to greatest. So the domain is the set of 2, 4, and 5. Those are all the possible x values in this particular relation. All the possible y values are 1, 3, and 1. But again, there's no point in stating 1 twice. That would be redundant. It's a possible value. It happens to be a possible value twice, but still it's a possible value, and we simply list it as such. So instead of saying that the range is 1, 3, and 1, we say the range is 1 and 3. And we put it in set notation form. Now, next we want to look at a discrete graph. A relation can be expressed this way. We have 4 distinct points, 4 discrete points, and so what we're going to do now is state the domain. Well, this point has an x value of -2. This point has an x value of -1. This point has an x value of 2, and this point has an x value of 4. They're discrete points. There's not a continuous interval here. So we can say that the domain is -2, -1, 2, and 4. Now next we see that we look at the y values in order to deal with the range. And the y values are 2. The y value of this point is 2. The y value of this point is -1. The y value of this point is 1. And the y value of this point is 2. So our possible y values are 2, -1, 1, and 2. But instead of writing 2, -1, 1, 2, we only list each number once and we put them in order from least to greatest. So we say that the range is the set of the numbers -1, 1, and 2. Alright, now the next one here is a continuous graph. Well, we see that we have an infinite number of points here. We also have an infinite number of x values to express in our domain, and we have an infinite number of y values to express in our range. So let's ask ourselves, what is the lowest possible x value that can be obtained in this graph? Well, that's going to coincide with the leftmost point. And we see that the leftmost point is at an x value of -3. So that's the leftmost point. Now from here, every x value in the function from here to infinity is to the right of that number. And they go on infinitely to the right. This arrow indicates that the graph will go infinitely to the right. And so we're going to have our domain go infinitely to the right. And so we're going to shade this number line in as such. And it might help us, now that we see that this is our domain, to write it in set notation form. And what we have is the set of all x's such that x is greater than -3. Now here, it looks like I put greater than or equal to -3. I meant to put greater than -3. But so this is our domain. The set of all x's such that x is greater than, not greater than or equal to, -3. And that coincides with the domain written here. Now let's look at our range. Our range, we look at our lowest possible y value, and our lowest possible y value is way down here. That coincides with the y value of -2. Now, as I move up the y-axis, I see that my curve has a point coinciding with each y value, at least one point. So for instance, at this y value, my curve has points coinciding with that y value. And as I continue up the y-axis, I see that at every possible value I get to on the y-axis, my curve has a point coinciding with that y value. So I realize, and since it goes up infinitely, I realize that the entire y-axis from a closed circle at -2 up infinitely is colored in. And if I think of this as a number line, it becomes easy for me to determine my range. And again, I made a mistake here, but it looks like the range is going to be the set of all y's. We tend to write, when we talk about ranges, we write in terms of y. The set of all y's such that y is greater than or equal to -2, and y is an element of the reals. Okay? So this vertical number line, our range can be given as the set of all y's such that y is greater than or equal to -2, and y is an element of the reals. Okay, now, the name of the course is functions, so you might be wondering what the heck is a function. Well, a function is a relation where every value of the independent variable corresponds with only one value of the dependent variable. So in layman's terms, what that means is every x-coordinate has one and only one y-coordinate attached to it. So if you have an x-coordinate of 2, there can only be one point possible associated with that x value of 2. If there's 2 points associated with that x value of 2, it's not a function. And as we'll see in a moment, what this means graphically is that every function passes the vertical line test, which means the vertical line test states that if a vertical line intersects the graph of a relation more than once, then it's not a function. We'll get to that in a moment. But first, pictorially, using a mapping diagram. Let's look at this mapping diagram right here. Is this a function? Well, an x value of 1 is associated with a y value of -3, and an x value of 2 is associated with a y value of 1 or a y value of 8. Because that x value of 2 is associated with two different y values, this mapping diagram does not represent a function. Let's look at this one. We have our x value of -3 associated with the y value of -5, an x value of -2 associated with a y value of 8, an x value of 2 associated with a y value of 8. Well, the y value of 8 is associated with two different x values, but that's okay. It's so long as each of these x values is only associated with one y value. So this is a function. It might not look at first because that 8 is used twice, but it's in the y column, and that's okay. As long as every time I give you an x value, you know the answer for the y value and there's only one possible answer, that's what makes it a function. Now, algebraically, we can see that, for example, the parabola y equals 3x squared minus 5x plus 1, this is going to be a function. And for example, if I give you any x value at all, and you plug it into this equation, you're only going to get one answer for y. You can't possibly get two different answers. So because you can only get one value for y for each valid value of x, it's a function. How about a circle like x squared plus y squared equals 9? This is not a function. And why is that? Well, for instance, if I gave you an x value of 0, y could be either -3 or +3. So in other words, we would not know the value of y given the value of x. If the value of x is 0, y is either -3 or +3. That uncertainty as to the value of y makes it not a function. So looking at things graphically, we can say the easiest way to determine if something is a function or not is to deal with it graphically. And we can recognize if it's a function looking at the graph by seeing if it passes the vertical line test. This is a function. The reason that this parabola is a function is because it passes the vertical line test. No matter what vertical line I draw through the graph, I only hit the graph one time. Therefore, it is a function. But how about this sideways parabola? Well, I look at this one, and if I draw a vertical line like this, that vertical line hits the graph 2 different times. Therefore, it's not a function. It fails the vertical line test because it hit the graph twice. Now, how about this right here? This is an odd looking relation. Is this relation a function? Well, I could draw a vertical line here and I only hit it once. And I could draw a vertical line here and I only hit it once. So on first glance we might say, yeah, that looks like it is a function. However, it's not. And the reason being, right at an x value of -2, if I draw a vertical line, I hit both of those closed circles right there. And the fact that I hit both of those closed circles means it can't be a function. And so that's how you look at things graphically. Algebraically, you can determine whether it's a function from its equation by determining whether more than one value, given a value of x, that there's more than one value of y. So for instance, in this question here, you have y equals plus or minus the square root of x minus 3 plus 5. That's not a function because we could put in a valid value for x from our domain and we would get 2 different values for y. We've seen a moment ago that circles are not good examples of functions. A straight line is a good example of a function because if I give you a valid value for x, there's only one valid value for y. Parabolas, like we learned about in grade 10, that open either up or down, are good examples of functions because if I give you a valid value for x, you only can get one valid value for y. With more practice, you become able to see these things for yourself. So a parabola that opens up or down passes the vertical line test. A parabola that opens sideways, however, not so much. So, as a final note, are these functions? Well, y equals 2x minus 5 is a function because when graphed, it's a straight line that is not vertical. I should say vertical. A vertical line isn't a function, but any other line is. x squared plus y squared equals 9 is